Welcome back to the video lecture series for Introduction to Additive Programming using Scala. In this video, I want us to start looking at binary search trees and using them to implement a map ADT. So we should talk about the general nature of a binary search tree and then probably remind ourselves what a map needs to be able to do. So this was the picture that we had for a general tree previously, and turns out the binary search tree is going to be a bit different from this. In a binary search tree, we want to have the restriction that all of the nodes can have at most two children. And we're going to call these two children special names. We're going to call them left and right. So if we draw a little, actually, do I want to do nodes? Nah. In addition, our binary search tree is going to have values in the nodes. And in particular, as I said, we're going to use this to implement a map, so those values also have a key. And the key needs to be ordered, so that, or have some sorting order to it, so that we can tell if something is less than or greater than something else. So because it's really simple for me to do in the drawing, let's say that our tree was using integers, and we'll start off and say that we have a 5. So a valid binary search tree might look something like this. So I have 5, and let's go 3 over here, and 7 over here. Now the rule for a binary search tree is that keys that are less go to the left and keys that are greater go to the right. So the 3 has to be over here to the left of the 7 and to the left of the 5, and the 7 has to be off to the right. Okay, that's not negotiable. If we were to try to swap these, then we would no longer have a BST. If I wanted to have, say, the value 4 in here, well, while it could go in lots of different configurations if things moved around, if I already have this structure and I'm going to add a 4 to it, well, the 4 is less than the 5, so it has to be over here, and it's greater than the 3, so the 4 has to come in right around there, and then it is off to the right side of the 3. Similarly, if we had a 2 in here, well, the 2 is less than the 5, and it's also less than the 3. So our 2 would be somewhere around in here, and we would connect that up. Okay. If I had a 6, it would go off to the left of the 7, and an 8 or a 9 would go to the right of the 7. That's the structure of a binary search tree, and this is what we enforce. In fact, I'll go ahead and I'll put in our 6 and our 8. It might be good practice for you to think about what the pre-order and post-order traversals of this would look like. So a pre-order for this particular tree, where we visit each node before we visit its children, starts with 5, and then 3, and then 2, it pops back up, 4, 7, 6, 8. That would be pre-order. If we wanted a post-order traversal, we would run down this edge and hit 2, 4, 3, 6, 8, 7, 5. Now in the case of a binary tree, another form of traversal is very well defined. This is an in-order traversal. Because we can only have 2 children, instead of being visited first or last, you could be visited in between. So we would go to the left, then we would visit, then we would go to the right. And what does that do for this tree? Well, we go to the left and we go to the left. This has no children, so we visit the 2, and then we pop back up. We've already visited the left, so we would then visit here and get the 3, and then we go to the right. 4, pop up. We'd finish the left, so 5, down, down, 6, 7, 8. Notice that on a proper binary search tree, when you do an in-order traversal, the things come out in order, in their proper sorted order. So how could we use this to make a map? Well, it's actually fairly simple. That in addition to having this key value, which is sorted, we would attach a second piece of data. And this makes an efficient map for us because as long as the tree is fairly well balanced, at each level, when we look and I say, okay, so let's say I'm looking for the 8 here, well, I can say 8 is bigger than 5, so I go to this side. And that immediately throws away everything that was over here. Have you ever seen anything like that before? Well, yes, in a previous chapter, set of videos, we talked about binary search. And a binary search did exactly that. It only worked for sorted arrays, but on the sorted array, it would look in the middle and then do a comparison and either throw away everything to the left or throw away everything to the right. That's effectively what a binary search tree does as well. And just like our binary search wound up having order log-in performance, as long as your binary search tree is balanced, you get log-in performance. So we can search and find things in log-in time. You can also add, because the routine that we just looked at to add here is to walk down and put something in, but the height of the tree, assuming it stays balanced, should scale as the log of the number of nodes. So that gives you an introduction to what a binary search tree looks like, as well as at least how we can add to them and how we could go searching in them. We'll come back in the next video and we'll start writing some code to do our binary search tree.